Okay, great. So I guess if you don't hear that, and I've started, there's a problem. Okay, and I was checking in Canvas a little while ago. The first homework being due a couple days ago. Let's see. Only 5 out of 9 have turned it in. I've mentioned that I'm a bit loose about deadlines, but what I generally will do is grade whatever I have over the weekend. Oh, and one person has already turned in a second homework. It's way ahead of the game there. Okay, so hopefully the rest of you can get that in soon. All right, now still on separation of variables, and I'm going to walk through an initial boundary value problem that's similar to what we've seen, but one of the boundary conditions presents a certain difficulty in obtaining a solution. We're still able to get a solution, except it's not as complete as we've seen in other examples. But the other thing about this example is the process of obtaining a solution is identical to what you've seen. So, and separation of variables, as you've seen, is a long, complicated process. So I think the more examples you see, the better, just to reinforce all the underlying concepts. Okay. So here's the problem in words. So we're still going to have a problem of heat equation like before, where we're modeling temperature in a rod of length 1. So our spatial domain will be x going from 0 to 1. And then for boundary conditions, at the left boundary, so x equals 0, the rod has a fixed temperature. And then for right boundary, x equals 1, we have a different sort of boundary condition. So instead of having a fixed temperature at that point, the rod is immersed in a solution of water that's maintained at this temperature, temperature 0. Okay. So, I'm going to rewrite this boundary condition. Oh, no, actually, I'll leave it the way it is. Okay. So, in terms of an equation here of boundary conditions, so here we have a type 1 boundary condition because the rod has a fixed temperature, and this is at temperature 0, at x equals 0. All right. At the right end, at x equals 1, this is a type 2 boundary condition. Now, the way that was written before was that on the left side of the equation, you have the what you have is the outward flux. And then on the right side, you would have the constant h times the difference between the temperature in the rod and the surrounding temperature, which in this case is also 0. So, we also have a coefficient of k that would normally go in front of this ux here, but here we're assuming a k is equal to 1. So if you look back at, I believe it's lesson 3, the lesson 3 notes. Actually, I'm going to pull that up now just so you can see what I'm referring to. Okay. Well, I need to unshare and reshare. I need to locate those notes. That would have been January 24th. Okay. Okay. Here's from the lesson pre-notes the general type 2 boundary conditions, where you have a temperature of a medium specified rather than the temperature of the object. So here so what we have here is the right side in both cases is the outward flux, and you can see the difference between the temperature of a rod and the temperature of the surrounding medium, which in this example is 0. And then that is set equal to minus KUX. Okay, so the outward flux is proportional to the inward normal derivative. So if we compare this boundary condition to what we have here, so K is equal to 1, the minus has been moved over here, and the medium temperature is 0. So it's that boundary condition. Okay. And then we need an initial condition. And for this example, we're going to assume that the temperature of a rod equals the position along the rod. In other words, the initial temperature at U of x0 will be x. So our PDE is a heat equation. There are no source terms of any kind, so this is a homogeneous PDE. Here are boundary conditions from above. And now our problem is completely specified. Now, the PDE is homogeneous, as I mentioned, it's constant coefficient. The boundary conditions are homogeneous, so we have 0 on the 0 on the right side. So the point is, because of all these conditions, this problem is suitable for separation of variables. So here I'll go through separation of variables process in the same way as in other examples, just dealing with the appropriate boundary conditions. So the separation of variables process starts out the same way as before. It only concerns the PDE, which is exactly the same as before. So we have these two ODEs. Now, here I have a different letter for the separation constant. Before I've used the letter K here. I'm using a different letter here because K is mentioned up here, K equals 1 for the median boundary condition on the right. So I have to use a different letter. That's one thing to be careful about. The students see a letter used for a certain purpose, having a certain meaning, and then somehow that meaning gets attached to that letter for all time. Don't do that. Because you only have so many letters to go around. So these are the same ODEs that we've had in previous separation of variables examples involving the heat equation. And for our spatial equation, solving for capital X and little x, the boundary conditions above apply. So here are the same boundary conditions applied to this ODE. Now, at this point, we don't know anything about mu, this separation constant. Is it positive, negative, or 0? Like before, we have to check. So first we consider a case where mu is positive. So we're solving this ODE where mu is positive, and recall my review of first order ODEs, or second order ODEs in this case. I'm sorry. I'm focusing on this ODE for this case. So because here we have alpha squared, so that's positive. If mu is also positive, our temporal ODE is going to have this solution. E to a positive constant times t. So here we have exponential growth. Could you imagine if you're modeling heat energy and what your model shows is that the amount of the temperature increases exponentially? I mean, that'd be like an apocalyptic sci-fi movie. Steam a trailer now, backward diffusion. And so this is a non-physical solution. So we have to exclude that possibility. So mu is not positive at least. Okay, are any questions up to this point? So we still have two more cases. Mu equals 0 and mu negative. If mu equals 0, then our spatial ODE reduces to x double prime equals 0. And we've seen this before. Capital X therefore has to be a linear function of x. Okay. So when that happens, we have to apply the boundary conditions. So if we plug in x equals 0, this has to be 0, which means b is 0. Now the other boundary condition is this one. We have a derivative plus h times the function value at x equals 1. So if I apply this boundary condition to this function, this is what I get, and that must equal 0. But if b must be 0 because of this equation, I account for that in here, capital A must also be 0. In other words, everything is 0. So the only way that you can satisfy this ODE and the boundary conditions for the case of mu equals 0 is to have a trivial solution 0. So that case also has to be excluded. So the only thing left is mu must be negative. So to reinforce that's negative, I'm going to write mu equals minus lambda squared. So this will definitely be at least a non-positive number. So in that case, this is what the solution to the time ODE is, that exponential, but now it's a decaying exponential, which is what we'd expect for a problem like this. And then for spatial ODE, this is our general solution. So it's some combination of a sine and cosine. In order to find out which, we need to you can apply the boundary conditions. Because at this point, I know that lambda is negative. I don't know, sorry, mu is negative. I don't know anything else about it. So we need the boundary condition to help narrow it down. Okay, now, and we also have these unknown constants, A, B, and C. Now, toward the end, we're going to take into account the initial data. For time being, we're just going to assume that capital A is 1. We're not going to lose any generality by doing that, because these two solutions are going to be multiplied together anyway. And then those are multiplied by a constant based on the initial data. So here we'll just take the exponential. But now we're going to apply the boundary conditions to this and see what happens. Okay. So here are the boundary conditions. All right, so at x equals 0, it's 0, at x equals 1, we have this. So what I'm going to do is, I'm going to go up here and plug in little x equals 0, little x equal 1, and plug this into these two equations. And here's what I get. So I've taken into account that sine of 0 is 0, cosine of 0 is 1. And so here, we immediately find from the left boundary condition that c is 0. So there's no cosine term. As for the sine term, so we have this. Okay. So one of these factors must be 0. B has to be non-zero. Otherwise, there's no sine term either. We once again have a trivial solution. So B has to be non-zero. So this has to be 0. So we can use this equation to solve for lambda. For anyone who's writing notes, always feel free to stop me, like if I need to scroll back or something. So I'll make sure that nothing gets left out. Okay. Now, up to this point, this example has proceeded much like other separation variable examples. Until now. Because we like to take this equation, where h is a given constant, and solve it for lambda. But we cannot. You can try all your algebraic and trigonometric tricks you know. It's not going to happen. Because we have a trigonometric function of lambda here, polynomial function of lambda here. When you have those mixed together in an equation, you're not going to be able to find an analytical solution for lambda. You're not going to be able to come up with a formula that says lambda equals this. So all we can do is settle for being able to solve this equation numerically. So there are various root finding methods for solving nonlinear equations. I actually teach about these in our numerical analysis courses, like Math 460. For example, Newton's method or bisection that you might have seen in calculus, depending on your instructor's preferences. So I won't get into that here. It's that I'll suffice to say that we do have solutions. There are actually infinitely many solutions. I won't be able to say what they are, except that certain. I believe in a textbook they mention a few, like to a certain number of decimal digits, but that's it. But that's what mathematical software is for. That can compute these. So now we have a function of x and t by multiplying these two together that satisfies the PDE and it also satisfies the boundary condition, provided that these values, lambda n, are the positive numbers that satisfy this equation. Now, I say positive because suppose lambda n is a positive number that is a solution of this equation. And now suppose that I replace lambda n throughout by minus lambda n. Well, the right side, of course, will be negated. The left side will also be negated because tangent is what's called an odd function. If you negate the argument of tangent, you negate the tangent. So in other words, if lambda n satisfies this equation, minus lambda n will too. And if I replace lambda n with minus lambda n in here, the exponential part will stay the same. The sign part will be negated. So you just negate the solution. It's still a solution. It still satisfies the PDE boundary conditions, but it's not linearly independent. In other words, these negative lambda values would be redundant. There's no need to incorporate them into our overall solution formula. So that's why we stick with the positive solutions. All right. Now, so we've taken care of the PDE and the boundary conditions. What's left are our initial conditions. But before I get into that, do we have any questions? Or any part of this I need to revisit? Okay. Here is our solution formula. So u of x t, the solution to our original problem, is going to be an infinite sum of the solutions that I just showed you that satisfy the PDE boundary conditions, but we multiply them by unknown constants, an. As in here I filled in what tn of t and xn of x are, so what we've just seen. So the only thing that's left is to find constants an, so that if I substitute in t equals 0, I will get the initial function, u of x0 is equal to x. So now, I go ahead and substitute t equals 0 in here throughout this equation. So if I set t equals 0 over here, I get u of x0. That's my initial condition, so the left side has to be x. On the right side, t equals 0. That only affects the exponential. So e to the 0 is 1. So that goes away, still have everything else. So this equation now has to be satisfied. We have to find a constant a sub n that will do that. So here's how we do that. And this is similar to what's seen in other examples, but again, something I want to reinforce. So what I do is I take this equation and multiply both sides of it by sine of lambda mx. So the same spatial solutions as before, I'm just using a different index, m instead of n. So I do that on both sides. And then I take the integral from 0 to 1. And I want to make clear why it's 0 to 1. That is the spatial domain of our initial boundary value problem. And because the integral is linear, I can pull out the summation, I can pull out an. So now I just need to work out these two integrals. Take into account whatever values of lambda m or lambda n I have. I'm not really going to talk about the left side one. So how you would do that, you would use integration by parts. The integral of u dv equals, etc., where x is plays the role of a u, and then sine lambda mx is dv. But it's a right side integral that's more interesting to us. Okay, yes?
Why do you multiply by sine lambda m again?
Oh, so the standard practice is whatever you have for your xn of x, that's what you multiply by. And what I'm going to show you for this problem, it actually applies in general. It provides a relatively easy way to find out the values of these constants. Okay. Now, when I work out this integral, it gets pretty ugly, or extremely ugly. So I'm not going to go through all the details here, but I'm going to point out ones of particular interest. First, I have a product of signs. That's not something that can readily be integrated. But if you use a trig identity, what's called a product to sum formula. I've used that in at least one other example. So now this product of signs can be written as a difference of cosines. This actually comes from the trig identity for the cosine of a sum or difference. Actually, one of my colleagues in this department pointed out that, of course, there's so many trig identities, but there's really only 3 that one needs to have off the top of their head. Well, okay, there's one trig identity that pretty much every student knows. Someone wrote it out, which is, oh, I mean just a trig identity.
Oh.
Sine squared.
Sine squared.
X plus.
Yeah, sine squared plus cosine squared equals 1. That's the one that I can count on students to know. Anything else is like, generally no. The other 2 are cosine of a sum or difference and then cosine of x plus or minus y, and then sine of x plus or minus y. If you know those 3, other ones can be derived from them. Maybe not every single one, but a lot of them can. And I found those 2, the cosine, other 2 cosine of sum or difference, to be useful in a lot of situations. And that can be used to derive what I've used here, a product of sum formula. So if you look at like any web page, like a Wikipedia page of trig identities, you'll see categories of product of sum formulas and sums of product formulas that come in handy now and then. And I can never remember those. I don't need to have them memorized because I have memorized the 3 that I mentioned, and I can use that to work out what these are. It's not convenient to like look them up in a table. You know, like if I'm stuck on 10 islands and I need to do some trig, you can't use the internet. You never know. So once I've applied that trig product sum formula, this is something that I can integrate. So I go ahead and do that. And once I get down to this point, this step, it seems like there's nothing more I can do, except there actually is, because so far I have not taken into account what I know about these lambdas. So to simplify this any further, I need to use this, that each of the lambdas satisfies this equation. So any lambda by itself, I can replace with minus h tangent of that lambda. And that's what I do going from this step to this step. So you can see like lambda n plus lambda m got replaced with the tangents of them, and then I get a minus that I put out front. Now, that may seem like I'm making the expression more complicated because I'm replacing a variable by its own minus its own tangent. There's also a factor of h here. But the reason I'm doing that is I have these other trig functions here. So now everything in the square brackets is a trigonometric expression. It's all only trig functions. So now I can try to simplify those. So then I rewrite each tangent as sine over cosine. And you can see how there are some opportunities for cancellation with some of these terms. And so now I go through some really ugly algebra, and look what happens. It all goes away. I find it amusing sometimes in some classes where I'll assign students to work with some difficult expression like this, and the goal is to simplify it as much as you can. And then they wind up with something really simple, like 0 or 1. You know, like, and there's like outrage about it. Like, that's it? This whole thing is 0? Are you proving all through this to get 1? Like, well, yeah. That's actually a good thing. So, in other words, when m is not equal to n, this integral goes away. So if I go back up here, I'm trying to solve this equation for all the an's. Here I have this infinite sum. But now what I've just shown you is that all of the terms in this summation are gone, except for when n equals m. So now I just need to look at that integral. So now I go ahead and do that. Now, I should mention though, what I'm just showing you here, since this integral is 0 when n is not equal to m, that tells me that these functions, sine of lambda nx, are orthogonal. So this is a very good property to have, that if you have a set of functions that are orthogonal, I'll give the general definition here. So orthogonality of functions has to be defined with respect to an integral. Okay. Oops, something went very wrong here. Okay. So I have to be real careful here. Real value functions. Fx, g of x, dx is 0. So that's what we have here. That this family of functions, they're all orthogonal. If you take any two different members of this family, then you get this. And I should have mentioned this once before, but I'll repeat it. Suppose you have two vectors in Rn. I need to give these names, U and V. In Rn are orthogonal if their dot product equals 0. It's the same idea. So orthogonality is a wonderful thing because it makes certain equations a whole lot easier to solve. It provides a whole lot of convenience. What is the dot product? Multiply corresponding components of these vectors and add them up. What we're doing here, we're multiplying values of f and g at corresponding x values, and in a way, adding them up because an integral is a limit of a Riemann sum. Okay. What about the case m equals n? So now we have sine squared of lambda mx. So here we use a different trig identity, a half angle formula. Also found to be useful in many situations. So now I have something that I can immediately integrate. So I go ahead and do that and simplify as much as I can. And I wind up with this. So now, if I go back to my equation that I had before, I had this. So for summation, all terms went away except for one where n equals m. So this an over here becomes an am right here. And then this integral, for the case of n equals m, is this expression. So I go ahead and put that here. Now I have exactly what I need. I now have this equal to this, and I can rearrange this equation to solve for, well, here's am, but I can also write an, as long as I'm consistent. So here's my formula for an. And now I can use that in here, and my initial boundary value problem is solved. So this satisfies PDE, boundary conditions, and initial conditions. Are there any questions about the solution process? Now, what you could do is, as I mentioned this in an earlier example, you can, since we have a decaying exponential here, as n increases, these exponentials become small quite quickly. So it's reasonable to approximate the solution by just taking your first few terms. So we go ahead and work out what these are, again, like numerically, and then just form the first few terms. Especially for larger t, that's a reasonable approximation of a solution. Now that concludes this example. I'm going to take a little time now to go over some general properties of initial boundary value problems such as this one. Now, here I'm focusing on the spatial ODE instead of the original PDE. So here we have our ODE and boundary conditions. So on the interval 0 to 1, which is what we worked on before, this is a special case of this kind of problem that's called a Sturm-Liouville. Not Liouville, Liouville, Sturm-Liouville problem. So it consists of this ODE in X, and then general boundary conditions. So in our example, P of X, the coefficient P of X was 1, Q of X was 0, this function W of X was 1. Here I have lambda squared, whereas here I have lambda. For general problem, we usually just use lambda. The squared here is only to reinforce that this expression is positive. But for a general case, that isn't necessarily true. Or it depends on the coefficients. I'll move this to a new page. Okay. Now, some terminology for you. This problem can only be solved for certain values of lambda. You'll have the ODE is infinitely many solutions, but the boundary conditions narrow down to a discrete set of solutions. So values of lambda for which this entire problem can be solved, has a solution, is called an eigenvalue. And then the solution y of x that you find corresponding to that eigenvalue is called an eigenfunction. I want to emphasize here, values of lambda which has a non-trivial solution, because I can always have 0 as a solution, and that's not interesting. Now, you've probably seen the term eigenvalue before in a whole other class. Anyone tell me where the term what class, what math class the term eigenvalue has already come up in? Yeah, it's a linear algebra concept. So I'll recall the definition for you. So if you have a situation like this, a matrix, square matrix A times a non-zero vector x is equal to a scalar lambda times the same vector x. Then lambda is an eigenvalue of A, and x is called is an eigenvector of A that's corresponding to lambda. So these concepts, eigenvalue and eigenvector for a matrix, eigenvalue and eigenfunction for this boundary value problem, are very closely related, because in both cases you have some kind of linear operator operating on some vector. In this case, your linear operator is a n by n matrix applied to vector in Rn. Here we have what's called a linear differential operator, something like differentiating, multiplying by p, or minus p, and differentiating again, plus multiplying by q. That is a differential operator. And the vector in this case is a function y of x. So it may sound strange to think of a function as a vector, but you can define vector spaces in which the vectors are functions. Because all you need to define a vector space are two operations, addition and scalar multiplication. And we can certainly perform those operations on functions, so functions define a vector space. And here we have a linear operator on such a space of functions, because what does the linear differential operator do? You apply to a function, and the result is another function. And linear operators have eigenvalues and eigenfunctions. It's all the same. And since linear algebra is generally easier to digest than other areas of mathematics, when I'm trying to understand something, or maybe even present it like for teaching, I try to relate it to something I know from linear algebra, and I find that helps me to understand it. And I find that classes or textbooks don't always draw those parallels, and I think they should. It makes things a lot easier. Now, for a matrix is a finite dimensional entity, and by a matrix as n eigenvalues. A differential operator like this one has countably infinite set of eigenvalues, lambda 1, lambda 2, and so forth, and they go up to infinity. So that's one property that this problem has, countably infinite solutions. That we use in problems like the example I just did, where your solution to an initial boundary value problem is a sum involving these infinitely many eigenvalues and the eigenfunctions that go with them. So that's something that holds true in general for a problem of this form. Also, as we've seen in examples, the eigenfunctions that you get from solving this problem are orthogonal. Now here I have a more general definition of orthogonal than I showed you before. So we're still in the interval 0 to 1, that's just for convenience. And so I define what's called an inner product of functions, which corresponds to the dot product of vectors in Rn that you would have seen in Calc 3. How do I define it? You multiply the functions together, and then if your original boundary value problem has a weight function here on the right side, then that weight function is incorporated in here. And if the integral turns out to be 0, the functions are orthogonal. So you have your eigenvalues, lambda 1, lambda 2, etc., and then you have your solutions, y1, y2, and so on. So the inner product of any two of these with different indices is going to be 0. So that's something you can take to the bank. That always happens for problems of this form. So this convenience that I had in this problem, where you have like these integrals magically turning out to be 0, that's an artifact, that's a feature of these kinds of boundary value problems. Okay, in a function w of x, we call that a weight function. Also, I won't get into details here, but it can be shown that the eigenvalues that you get are always real. That's not something you can always take for granted. If you have a matrix, for instance, a matrix of real entries, the eigenvalues could be complex. But in this case, it's known that they're real, which is is what you want because you're trying to find real value solutions to your PDEs. It's also known that if a coefficient, if I go back, if this coefficient P is strictly positive, and this coefficient is at least non-negative, and it's not zero everywhere, then it can be guaranteed that the eigenvalues are not only real, they're actually strictly positive. We actually have this property. Here I've defined the notation for a differential operator. So L is the operator, capital L is the operator, applied to a function y, performs this operation. And it can be shown that if I use this inner product that's defined here, and compute the inner product of u and LU, as long as the function u is non-zero, the result will be strictly positive. And that can be shown using integration by parts. There's an analog for this in linear algebra. If you have a matrix A that's symmetric and it satisfies this dot product of vector x and A times x, and you can see similar to inner product of u with differential operator applied to u. If that is strictly positive, we say the matrix is positive definite. So this notion of a matrix being positive definite corresponds closely to the notion of a differential operator being positive definite. And in the language of linear operators, it's exactly the same concept I'm showing you. It's applied to two very different vector spaces. So in fact, there's one more parallel. So Sturm Liouville problem is said to be self-adjoint, has real eigenvalues. That's the same idea as a symmetric matrix has real eigenvalues and orthogonal eigenvectors, which corresponds to the eigenfunctions of a Sturm Liouville problem, also being orthogonal for appropriate inner products in each situation. So there are a lot of correspondences like these between what happens with linear differential equations and linear algebra. And to me, it's kind of unfortunate that for our first ODE course, Math 285, linear algebra is not a prerequisite. Because I find for that class, linear algebra being very useful in deriving a lot of the solution techniques that come up in that class. But then I start talking about, I even whispered through linear algebra, and the students are like, hey, we're not supposed to have to know that. Like, sorry. Okay. All right. So what you see in the example I showed you and the other examples from previous classes, where we have things work out nicely in terms of being able to find all the unknown coefficients we need. These aren't flukes. It's how these problems work in general. I should mention that, so we have a class, it actually hasn't been offered in a while. It's Math 415 or 515 for graduate students. That is you can think of it as a second ODE course. It's called differential equations and special functions. It used to be required for physics students. It's not anymore because it hasn't been offered lately. I'm not sure which is the chicken and which is the egg in that one. And so that class gets into aspects of ODEs related to mathematical physics, certain ODEs that are interested in that field. In fact, the textbook is a handbook of mathematical physics. And there's a lot more discussion of these general kind of problems and their properties and certain functions of interest like in physics, like algebraic polynomials, Bessel functions, things like that. Tentatively, I am assigned to teach that class in the fall. The first time it's been offered since 2016. So if you find something interesting and you're a math or physics major, then it might be worth your while. So, and it qualifies as a math elective. Okay. Now, do we have any questions about this or any homework problems? Yes.
Lesson 5, number 1 and 3.
Lesson 5. Okay. Okay. Okay, so number 1 first. Okay, so what you're doing in this case is you're just going to be taking the necessary derivatives of this and just making sure that everything matches up.
So the derivative in regards to x and to t?
Yes, so first derivative with respect to t, second derivative with respect to x. Okay. And then for the other one, Fourier sine expansion of this function on the interval 0 to 1. So we go to, because this actually came up in the first separation of variables example that I did. So what you're doing is you're computing this, so equation 5, where in this case 5x is equal to 1. And just working out the integrals. Now, the thing to keep in mind is that depending on the value of n, for any integer n, you're going to get different expressions. And here you take into account that, I'll write this into the notes. So this expression, cosine of n times pi, this only comes up fairly often, in fact, is equal to -1 to the n. Because what you'll end up with is like a piecewise formula. That you get one expression for n odd, one expression for n even. Okay, assigned all 5 problems. Apparently I was feeling evil that day. Yes?
So what does it mean when it says like draw the first 3 to 4 terms? Is it going to be like draw as a graph or just list out the terms?
All right, so what that means is, see that the example was written out. Okay.
If there's like some cosine and sine graphs earlier, so I'm sure.
Yeah, so here's what a Fourier sine series looks like on the interval 0 to 1. So after you work out what your coefficients will be from the first part of the problem, then you'd be taking some portion like this and graphing that, but cutting it off at this point. Okay. And so the Fourier sine series, okay, I'm going to comment about that in the notes. Okay. That so graphing first few terms, what you get should kind of converge to a function you're taking the Fourier series up. Now, the reason why it won't truly converge is if you have a sum of this kind, can you tell me what would happen to this expression? Let's focus on this. Regardless of the values of these a's here, if you plug in x equals 0 or x equals 1, what would you get? Sorry, I can't hear.
0.
Yeah, so you get 0. So any function of this form is going to be 0 at the endpoints, x equals 0, x equals 1. And that's why we use this kind of series for PDEs that have those kind of boundary conditions. Like if you have a type 1 boundary condition that's homogeneous, so the solution is equal to 0 at both endpoints, this is the ideal kind of series to use. But you're trying to take this Fourier sine series of a function that's not 0 at the boundaries, because it's equal to 1 everywhere. So when you evaluate 3 or 4 terms, it will be 0 at the boundaries, but hopefully in the interior, it'll start to at least kind of look like the function 1. But so a way this, if you were to take as many terms as possible, like a zillion of them, what you would see is it is converging to 1 in the interior, but not at the boundaries. You tend to see some high frequency oscillations. It's called Gibbs phenomenon. And you're only taking a few terms, so don't expect very much. Still got time? Any others? Yeah, so in fact, once you have the coefficients from here, you can use them down here. So there's not much work to do after that. I've mentioned this kind of case before, that when you have your initial data in a nice form like this, that makes it particularly easy to get the coefficients. So one of the examples I wrote up in the notes is an example of that. Except that example had cosines, but it's the same idea. Anything more, whether it's from here or out in online land?
You said earlier, like you could use cosine n times pi to equal to like -1 to the power of n or something.
Yeah.
How do we do that if like x is also part of the integral?
Well, the reason why I mentioned this expression is, okay, it carries the integral, and you're plugging in the limits 0 and 1, so the x is going. So your final result is not going to have an x in it. Okay, going once, going twice. Okay.